So let me take the next 30 to 40 minutes to give you a glimpse at the future. And for those of you that are at home in front of your screens, I know it can be quite tough to focus on your presentation, on the presentation, if the speaker is not actually in front of you. Nevertheless, I ask you to give me your full attention for the next 30 minutes, because the more you put inside, the more you will also get out of this presentation. And I promise I made it lively. I have included a few short videos, so that's not only me talking continuously for 30 to 40 minutes. All right, I divided the talk in 3 different parts. So we will start with a general introduction where innovation is actually headed, and then look at the technologies that you should watch here at Leonard that will give you an idea of maybe how the future will look like. And then the last minutes I dedicated to a Q&A with you where we can discuss a bit the consequences around the ideas that I present to you. And I think you're all very familiar with Hello Tomorrow, so I won't give another intro of us, just one aspect why we are suited to answer those questions that you see on the screen is that we are building a collaborative deep tech ecosystem, and key stakeholders of that ecosystem are young ventures, young deep tech ventures, and sourcing them and integrating them in our network. This is a key activity of Hello Tomorrow. And by curating those networks, we get good insights into current technology trends and innovation trends from where I will report to you. So where's innovation headed? And for this, I want to take you back actually to my hometown, Berlin, about 60 years ago. We are at the high times of the Cold War, where Soviet Union and the US, the tanks of each of those countries are facing each other. And this gave rise to the space race. The urge of both systems to overcome each other. Basically, each system set the challenge, we want to be first at the moon. That gave rise to the information age we are currently in, because the technologies that were built for the space race are now the foundations of our information age. So I want you to take from here that society drives innovation. We are the ones that determine the direction. And now when we jump into 2021, fortunately, we are not anymore in the times of the Cold War, while we have other issues here as society, namely our non-sustainable lifestyle that endangers the health of our planet, and some of our society faces great inequalities. And so in 2015, the UN came together on behalf of all the people and came up with those 17 Sustainable Development Goals. And as you can see on the right-hand side of your screen, deep tech startups actually address those goals. And this is not a surprise to me, because deep tech founders are coming right out of the middle of our society. So obviously, those technologies and innovations they work on, they target those Sustainable Development Goals. However, as you can also clearly see, is that some of those goals are more often targeted than others. So namely, good health and well-being is one of the most frequently addressed Sustainable Development Goals, but also affordable and clean energy or the climate action Sustainable Development Goals that are addressed. On the other hand, peace, justice, and strong institutions, so goal number 17 or 16, is actually hardly addressed by deep tech startups. Now, same 17 Sustainable Development Goals, but I circled other ones. Those ones I circled here that you see in this turquoise color are the ones that are directly related to the health of our planet. And I want to emphasize those ones because the health of our planet is no longer an ecological issue. It has become a societal one. And I want to read to you a quote from one of our last publications. It says, "Humans have become the single biggest driver of planetary change affecting our own life support system, the Earth. In order to not further endanger the foundations of our own lives, we need to learn to live within the means of our planet. And consequently, as an outcome, every single innovation faces a twofold challenge. It needs to be energy efficient, renewable, non-polluting, as well as obviously offer significant value in the respective field." And I'm very happy to tell you that about 55% of our deep tech ventures in our current cohort are exactly aiming at that, enabling humanity to thrive within our planet limits. So now I think I've set the scene. So innovation and the sustainability angle is the one that really drives current innovation. And which technologies do I think you guys need to watch? There's 4 key technology fields in focus where we see great dynamics. So it's synthetic biology, energy, advanced computing, and new materials. And they result in 3 paradigm shifts. One, you've heard from Arnaud before, nature is becoming a manufacturing partner rather than just an output that we use. Then we are decarbonizing our energy supply thanks to new energy storage solutions. And we are trading atoms for bits wherever we can. So we run more on a data and simulation-based resource management scheme that will be beneficial to our environment. Let's start with the first paradigm shift. So you see here on the left-hand side of your screen that the current economy, usually we extract fossil fuels and raw materials. We use large amounts of energy to shape them, to refine them, and we get new materials and refined chemicals out of it. And as Arnaud mentioned, the future economy looks quite different. So we will use CO2 or sugar as feedstocks for microbes that are engineered to produce us new materials, designer nutrition, or refined chemicals. So we really use microbes as mini molecular factories. And to showcase to you how this is done in a massive parallel fashion, I have a little video prepared. Maybe we can play that one. So it's Cymergen. The CEO of Cymergen, no, one before, the slide before. Yes, there we go.
I'm Josh Hoffman. I'm the co-founder and CEO of Cymergen. Cymergen is rewriting the potential of biology. We're leveraging the power of automation and machine learning to do work that frankly was impossible before, to help understand the vast quantity of data that comes from large-scale biological experimentation, and then to help predict the set of things we should do going forward.
They're taking principles that have long been utilized in other areas of engineering, particularly things like chip design and computer design, and bringing it to biology.
We use robots and machine learning algorithms to reliably design, engineer, and optimize microbes. Our work has the potential to revolutionize chemicals and materials, agriculture, including animal health, human health, even things as diverse as waste management or mining. So we really think this has the potential to change the entire economy.
They're taking the traditional way that you would create new materials in a lab or traditional manufacturing based in really right out of the Industrial Revolution and try to take that into much smaller, faster testing, data replicated environments.
What biologists have done and still largely do today is they'll come up with an idea for how something works, and then they would go into the lab, would do the set of experiments that allow them to test the hypothesis. We allow scientists to do their work in a wholly different way. They can survey biospace, genome space, in a way they simply couldn't if they were doing it by hand.
So you got a glimpse at that we use process automation and AI to make sense out of all those biological data. But I'm not sure how familiar you are with actually what means engineering biology at scale and what are the scope and the potential of it. So engineering biology means writing, editing, and reading genetic code. And on the right-hand side of your screen, you have a little scheme that should illustrate to you the difference between natural evolution and what an engineer can do when engineering biology. So you know that the concept of natural evolution is that if a mutation in a species is beneficial to this species or to this individual, it will pass throughout the whole species, and you can explore what I would call local optimas. However, if the mutation conveys a deficit to the species, this mutation will not, basically the species won't survive because it's in competition for food and maybe falls prey to another species. So there's no way in natural evolution that you go through several, let's say, minima to get actually to the optimum, to the global optimum. But the engineer can do it as long or as soon as the engineer knows the whole design space and knows the design principles that underlie biology, you can go from a local optimum to a global one and really do amazing stuff. And this is what I show to you on the next slide. So this might be not something you immediately see the relevance for you, but I will come to it after the video. So that's a company from Finland that produces food from air, nothing else, just from air, using microbes. So if we could play that video, please.
The protein that we produce has its origins in a type of microbe that can be found in the nature. In order to multiply one microbe into billions and billions, we start by hand-picking samples from nature and taking these into our lab. Here in our laboratory, we take the samples we have collected from nature in order to screen for the best organisms. These samples are incubated in flasks in suitable conditions, which help the desired organisms to grow and multiply. So we continue to cultivate the mixture and increase the cultivation size step by step so that eventually it's ready to be transferred into the bioreactor. However, before we visit the bioreactor, let's have a look at another piece of the puzzle. In order for the microbes to grow in the bioreactor, they will need food. This here is our air capture device. The purpose of this device is to capture CO2 and water from air. The water that is collected is then split with electricity to hydrogen and oxygen gases. The CO2, hydrogen, and oxygen are then fed into our continuous bioreactor. This here is our bioreactor. There we cultivate the organism which we have discovered from nature. The main nutrients that we are using here, CO2 and water, we capture from air. And then we are also supplying with minerals, including ammonia, which is then the source for nitrogen. The organism that we are using does actually the heavy lifting in this process. So we are only letting it fulfill its purpose, the continuation of life. Next, we move on to something pretty exciting, the harvesting. In harvesting, since the microbiomass contains a lot of water, we need to remove the excess water. And we do it by centrifugal separator here, and the resulting slurry is then ready for drying. Finally, we turn the cell mass slurry into a dried powder. This entirely new protein is called Zoline, and it's completely natural and sustainable.
Okay, so we had a little screen failure here in the room, but I hope you could all see at home in front of your screens. So what you've seen here is a company that uses not much more than CO2, water, and some minerals to produce designer nutrition. And I still owe you why I think that's relevant to Leonard. It's because this technology that's called precision fermentation will provide protein more sustainably, in particular by using 10 to 25 times less feedstock, 10 times less water, 100 times less land, and 5 times less energy compared with protein sourced from cows. And I think this is the 100 times less land is key here, because I'm not advocating that that should be used to construct new cities, at least not entirely, but I think some of it should be repurposed to recreate forests and wild savannas. But some of it might actually be accessible to urban developers. So I think that's of interest to you. One more example from the synthetic biology sphere, which I think is amazing. A company from Sweden called Swedish Algae Factory has engineered algae. So you see a picture here on your screen, and look at the scale bar, it's 5 micrometers large. You see here an algae that is covered by a silica shell. And this company is harvesting the silica shell at the end of the lifetime of the algae and produces non-porous silica that can be used in solar panels and renders those solar panels up to 40% more efficient. Now you ask, why is that? And the answer is because nature has over millions and millions of years optimized this silica shell to trap light, because algae is a photosynthetic organism, meaning it needs light to survive, and trap light to produce all its building blocks for life. And in order to do so, it has optimized the silica shell. And at the same time, it filters out the very energetic parts of light, because those could cause mutations in its genome and cause it to die. So UVA and UVB is filtered out by that type of silica, so it can also be used in personal care products as sun blockers. Something that is probably more, you are more familiar with is decarbonizing, our efforts to decarbonize the energy that we are currently using. So the current economy still, to a way too large extent, relies on fossil fuels and biomass that we burn to create energy while emitting large amounts of CO2. The future looks different. So as already of today, we use in some parts of this world and to some extent renewables to produce electricity, but we will also capture waste heat to produce electricity and store electricity if it's in surplus. Looking at Craft Block, it's another video. Let's play it.
Climate change is one of the greatest challenges humanity has to face at present. It takes more than wind and sun to master energy transition. We need innovative solutions that generate energy and fundamentally change how we use energy. This means we need to provide energy whenever the user needs it. This is where Craft Block comes into play. Craft Block is multi-purpose high-temperature energy storage. The material, which is made out of recycled products, can store heat from different heat transfer media at temperature levels of up to 1300 degrees centigrade. The modular units can be operated individually or together as large volume systems, as either stationary or mobile applications.
Craft Block stores up to 1.2 megawatt hour heat per cubic meter of storage space, up to 15,000 cycles. This is much more ecological, efficient, and durable than other energy storage sources. The secret to Craft Block's efficiency is its extremely productive granulate. In addition to its high storage capacity, it offers a very low CO2 footprint due to the high proportion of recycled materials. It can also be easily adjusted to various applications in the field of power and waste heat, such as power to X and heat to X.
So the solution here from Craft Block is really geared towards heat-intense industries, such as the steel industry that operates at high temperatures. And these phosphorus granules that you've just seen allow allow the storage of such heat, and then putting it back into the system either as heat or as electricity. The next solution, and here you're really fortunate because Christina, the CEO of Agora Energy Technologies, will pitch to you in a few minutes from now. It's a grid-scale battery, so nothing too exciting about a battery you may think, but it has a dual function because it utilizes CO2 at the same time. So it's a CO2 redox flow battery. That means that during the charging and discharging cycle, it takes CO2 coming from flue gas and transforms it into a carbonate, which is a mineral basically. So it's a non-gaseous form of CO2 that can be almost like this deposed in nature. And I won't go into too much details here as she will present that to you in person in a few minutes. But keep in mind that batteries do not necessarily need only to store energy, but here we have a dual function of CO2 transformation. And the third, so besides Craft Block and Agora, the third obvious energy storage medium that there is outside is hydrogen. And I don't want to go into too much detail looking at the scheme here behind me. It just showcases how in 2030, if all the national plans of the EU countries are implemented, the hydrogen economy could look like. But the basic idea is that you use renewables to power electrolyzers that will split water into oxygen and hydrogen. The hydrogen can be isolated and stored and then powers our industries, but also our buildings and the transport means. And key for the transformation of hydrogen back to electricity are fuel cells. And those fuel cells are currently a bottleneck. And Celadine Technology, who is the winner of our environment track, actually works on improving the efficiency of those fuel cells. They have developed a new membrane that allows them to run those fuel cells at almost double the temperature, which results in double the efficiency. Coming to the last paradigm shift, so where we trade atoms for bits. So far, to come up with new materials, it was a very tedious and labor-intense process where we had to experiment a lot in labs to get to new materials. And the real power of the digital world, advanced computing like quantum computing or AI, will be that we can use them and harness their power in generative design and simulations. So we can actually run in silico tests and think about materials and optimize materials for sustainable properties, for example, and only take the best lead candidates into the lab and run experiments with them. So that should result in reduced material consumption, so meaning a lower environmental footprint, as well as shorter development time and lower costs. And Arnaud had that in his presentation as well. So that's Cabotics, a company from the US that has developed a hyper-automated lab where an AI basically feeds a robot to synthesize or with ideas to synthesize chemistry and chemical molecules of up to 70 atoms. And the results are fed back into the AI for another round. And this company has geared its AI to explore the chemical space. So the chemical space is up to 10 to the 60 possible chemical entities are there when we are just talking about 1 to 70 atoms. And we have today about several 100 million of those chemical possibilities explored. So meaning trillions of trillions of trillions are still remain unexplored, and Cabotics is trying to automatize that and come to new chemistries and materials that way. And why are new materials of such interest? And we had the question around the cement industry, so we could play one more time a video.
Around the world, almost 7 million people move to or are born in cities every month, which can be super efficient because when people live close to each other, it's easier to move people, power, water, and basically everything else around. But it's also a problem. In order to build all the buildings and infrastructure these new city dwellers will need, the equivalent of a new New York City every single month for the next 40 years, we're going to need a lot of concrete. And for the health of the planet, concrete is a 1-2 punch. Well, technically cement is the heavy hitter. It's the thing that, cements the basic ingredients of concrete, sand, rocks, and water, together into a single useful material. And it's a mean source of planet-warming carbon dioxide. Cement's 1-2 punch comes from how it's made. First, we have to heat limestone, which typically requires us to use lots of fossil fuels, which emit CO2. Second, once we do that, the limestone chemically breaks down into lime, which goes into the cement along with some other stuff, and carbon dioxide, which goes into the air. In most industrial processes, the energy used to run machines and heat stuff up is the overwhelming source of carbon dioxide. But with cement, when the limestone itself breaks down, it releases even more CO2 than all the other parts put together. All told, for every ton of cement we make, almost a ton of CO2 gets released. Today, cement's double whammy leaves it responsible for 8% of humanity's carbon dioxide emissions. That's more than airplanes, ships, and long-distance trucking put together. And as we keep on building a new New York City each month, the emissions from cement are only going to go up. So, what to do about cement? We could build some of these new buildings out of other materials, and we also could use less cement per building. For the cement we do use, we could try to manufacture and heat it using renewable sources. And these things would certainly help. But the real game changer would be to stop using limestone itself in cement. Then it wouldn't release CO2 when it breaks down. And there actually are alternatives out there already, some of which can reduce the amount of limestone needed, and others that can replace limestone completely. So far, most of these alternatives are either too expensive to make, or too early in development, or are being adopted tentatively because concrete is such an important structural material. But some alternative cements are already being used successfully in major buildings and bridges around the world. And when we use cement with less limestone, or with no limestone at all, as the foundation for all of our new cities, we'll reap some seriously concrete benefits.
And that's exactly what Nanogens from Switzerland is doing. So they have developed a nano additive that can be added to the cement or to the concrete formation process, and that reduces the amount of limestone that is needed, and thereby decreasing the emissions of up to 50%. The very last company, deep tech venture, I want to introduce to you that will also pitch in a few minutes from now is carbon upcycling technologies. So these guys have developed a new chemistry that allows fly ash to absorb more CO2. In that way, rendering the construction industry actually into a non-polluting, or let's say less polluting industry. So if we could play the last video, thank you.
Carbon upcycling technologies is basically based on a chemical adsorption process. So basically what that means is we take low-grade carbon, something like graphite or coke or coal, and we create surface area on that so that it absorbs CO2. So sort of the analogy that we've always tried to use is like a piece of cheese. So usually you think about it having holes. You know, that's kind of the stereotypical piece of cheese. But think about the piece of cheese in our process being a monolith, like with no holes going in. But when it comes out of the process, it's got all these little holes which are now entrapping CO2. What we've spent a lot of time on in the last couple of years is proving that that's stable capture. So it's not that, you know, you move that piece of cheese or the graphite or the coal in our instance around, and that CO2 just over time releases back to the atmosphere. And what we found is that it's actually stable up to 2 times the boiling point of water. So up to 200 Celsius, which is quite stable. The more interesting part of the technology is people have looked at adsorption for hundreds of years. I mean, we've used it actually for thousands of years as humanity. But when it comes to the CO2 challenge, in the last few decades, everyone has always had a step where you release the CO2 back because, you know, the piece of cheese with that CO2 in it, no one wants that. And what's different about our process is that you can actually use that filler with the CO2 in place as a reinforcing agent for polymers, so plastics, for concrete products, as well as for asphalt and coatings.
So you can ask your questions in a few minutes from now directly to them. But what they actually achieve is that they can sequester 50 to 250 kilograms of CO2 from the atmosphere per ton of product. And I want to finish the presentation. If you could switch to the last slide. Could you switch to the last slide? The clicker doesn't work anymore. Or maybe it's just a retour screen for me. I still see the carbon upcycling technologies. Is the last slide coming up? Yes, perfect. Thank you very much. So I just want to end my presentation with a quote from Al Gore that says, "We believe that we are in the early stages of a sustainability revolution, one that will be larger than the Industrial Revolution with the speed of the digital revolution. We believe it's the biggest investing opportunity in the history of the world and the biggest business opportunity in the history of the world." And with this, I'm happy to take any questions, or if you have to take your time to think about a few things that you heard today, please reach out to me via email. Thank you very much.
Thank you, Nicholas. Thank you for this great presentation. There again, giving us a lot of insights about what's actually going on. Actually, we still have we have a huge program and little time for questions. So I was thinking maybe we'll jump into the last sequence, which anyway, you are also in charge of leading this afternoon. Just a word, I shared on the chat a link towards a study that has been published by Leonard back in March 2020 with Good Tech Lab. We issued this emerging trends presentation, including a lot of those emerging solutions that concur to the realization of, well, call it climate tech, call it clean tech. They're gaining a lot of echo these days, and there's a lot of these solutions that are presented in this presentation, which is available from our website. No, we have 4 of these solutions and 4 entrepreneurs that are going to pitch their solutions in very short times. And I'll let you tell us, well, lead us through these presentations, which are originally based on the finalists and winner of the various categories of the Global Challenge.
Thank you. Happy to do so. So the first startup that is coming up, and I hope is connected, waiting for us, is the winner of the Hello Tomorrow, the grand winner of the Hello Tomorrow 2020 summit. So it is likely Christina from Canada who will pitch her dual function battery. Remember, the CO2 net sink while storing energy at grid scale. Christina, can you hear us?
Yes, I can hear you. Hello, everybody.
Hello.
How and
are you
happy
doing?
New Year. Happy New Resilient and Happy New Year ahead.
Thank you. You too. Christina, you know, you have about 15 minutes of time, so we would like you to maybe take 5 minutes. I mean, there's no stopwatch running, but around 5 minutes of you explaining one more time your solution. I did my best, but you can do that way better, I'm sure. And just inform the people a bit around what you're doing, and then we will have 10 minutes for a Q&A.
Thank you very much.
All yours.
Thank you very much for the introduction. I am Christina Genge. I'm the co-founder and CEO of Agora Energy Technologies. And I will present today our efforts to advance the energy transition via a totally new technology that enables a carbon negative electricity production. So I don't have to give more introduction to our 400 gigaton CO2 challenge or opportunity. If you are a deep tech startup, it's more of an opportunity than a challenge. But anyway, we look at it by virtue of its 35% of share of the global GHG emissions, the energy system must undergo a transition in the next decade. And decarbonizing the grid and providing dispatchable renewable electricity requires robust and flexible and inexpensive energy storage. And equally important is to actually find uses for the large CO2 emissions that we have at hand, because developments in the field are starting, but they are still somewhat limited in scope. So while we were pitching in December for Hello Tomorrow, the news was that Google actually embraced the new battery revolution. So there is obviously a global and synergistic efforts to move toward a more sustainable society. But first, I want to take a look and to present you what's the reality of the batteries today. So one thing that you would observe looking on this first line is all of them are metals, and they range in developments from the 1800s, starting with the zinc batteries, to the more recent lithium and vanadium type of batteries. But these are the market entries. All of them are metal. Metals obviously are mined, and mining is associated with tremendous CO2 equivalent emissions. And what is more striking, it's not striking, it's expected, that as demand increases and as we will embrace adoption of this battery, we expect a high price fluctuation and probably supply chain limitation. So our question was, what if we would utilize actually CO2 instead of these metals as a vehicle for energy storage? So what we obtain here, the result would be a scalable battery technologies that enable either a carbon negative or a carbon neutral electricity. And to talk about the economics, we can look at the current price of CO2 capture and purification versus the price of lithium. We are talking 2 orders of magnitude. This in turn is expected to drive the battery price down. So what we propose with our new technology is basically the CO2 redox flow battery. And I won't insist more in the battery characteristics. What is important for those of you who don't know is that these batteries have the battery stack and actually module inside the battery, while the storage of electrolytes are outside the battery. This is a key advantage because they impart the battery longevity and flexibility in scale up. So how the battery works? Basically, during the charging, CO2 that is purified and captured from an emitter in the presence of renewable is charging the battery. During discharging, electricity, like in any other battery, is produced, but we also have the option to produce carbonates. So on this node, by building this battery, we are producing electricity, which can be monetized, as well as high value market products. So when we started this battery way back, we were really expecting that the market will not really make concession for our products. So the value of what we create has to be there. I want to, I know this slide is crowded, but I want to present you the advantages of this battery. So what make our technology unique is the manner we design our system to capitalize in a battery that have a much superior performance over all the existing metal batteries on the field. So if we look at the three entries of lithium-ion, vanadium, and zinc batteries out there, we try to have a high energy density comparable to lithium, long lifespan comparable to vanadium, flexible, long storage duration, and what makes this battery extremely competitive is that it can store energy for hours, days, or even months. And this is not magic. This is the manner you select what type of energy storage media you have. For instance, in the conversion of CO2 to fomate, you have a substance and a storage media that is temperature resilient from -30 to 80. It has up to 6-8 months of shelf life. So this is how we can increase the duration of storage for and extend to seasonal capacity. Now, at the bottom part, I presented a little bit what is the CO2 mitigation potential of such a battery in addition to using CO2. Of course, no metal mining, no CO2. But also if we compare it, say, with the direct air capture that are expected to, or we expect that they will have a large contribution to mitigating the CO2 emission. So while on a direct capture unit, you have a high footprint, you consume energy, and you spend for each and every CO2 that is mitigated. With such a battery, you are actually make a profit, a high profit by utilizing the CO2. You have a low print, and you enable the negative electricity generation. Another aspect that was not much talk about is the carbonite production that we have in our system. To date, the Solvay process is the oldest and most embedded, and they have dominance in the world for carbonate production. The Solvay process comes with the price of quite a high CO2 tax. It's quite a dirty process. So here we have a battery that has a byproduct, a carbonate, which is really a result of mineralization from CO2 to carbonate. I won't insist much on the revenue model, but we can expect that such a battery has entry in two markets simultaneously, the storage and the CO2 space. And for instance, as an example, if we take a 5 megawatt battery, we could capitalize on the licensing on the emitter, say the emitter is a cement plant, the electricity revenue by energy arbitrage, and of course the carbonite revenue, which is the highest. So for a 20 years operation, which is standard for a redox flow battery, that's about $250,000. Or if we look, for instance, at a deployment by doubling the batteries between 2025 to 2030 to up to 30 batteries, that would be a 5-year revenue of cumulative revenue of about $1.3 billion, which sounds a lot, but it's about 0.2% of the market. So it goes without saying that our intent with this battery is to look at CO2 as a business opportunity. I explained already the portion on the right-hand side and how we go about it, but we have to think at it that at the end, the output of this battery is actually electricity that can be sent to the grid or to a microgrid with all its advantages to be deployed for electric vehicle charges or household. And the most important aspect of this battery perhaps is actually who are the potential adopters. And if you really think of it, everybody who either emits large amounts of CO2 or needs large amounts of energy. I will leave you with a last example because somebody asked about the opportunity for cement industry and building materials. So for instance, the example would be if you have our CO2 redox flow battery. So the CO2 emitted is captured and purified, is the raw material entering the battery. In the presence of renewable, the battery is charging. During discharge, electricity can be sent back to the plant or to external operation on the grounds, for instance, to electrify the fleet of such a cement plant. And in addition, if we have the carbonates, whatever is perhaps not sold on the market, in order to not overflow the market, what we can do is actually to use these carbonates back to the flue gas and do a flue gas treatment. So I will end my presentation by saying that really what drives our innovation is what was mentioned by the speakers many times before. It's really this conviction of ours that any future developments have to be compatible with existing resources, has to work within the planetary boundaries, and we actually see ourselves as key enablers for this. And during the 2020, all the awards we received were actually related to totally different areas of our technologies. And from the utilities, CLP from Hong Kong, they were looking at the utilities aspect, to charging the future competition by Impact Canada, which is really looking at transportation, but from the perspective of how we can provide cheap electricity for the electric vehicle, and of course to the built environment, where we were part of the Lafarge Holcim activities and the CO2 Club. And on this note, we think that we actually have quite an overlap with the Vinci Group, their model being and intent being to meet the global challenges. So I would be more than happy to discuss further if you are interested. Thank you.
Thank you very much, Christina. Thank you very much for your presentation. Really exciting to hear. We have I think we have a couple of minutes for a few questions here from Leonard, straight from Paris to you. When hearing about all of this, what comes to my mind is, where did you get your idea from? I mean, there's so many advantages to this. Can you elaborate a bit more on this ideation process? How did you come up to use CO2? I mean, what was your primary driver for that?
Well, there is a long story and a short story. First of all, I'm a chemical engineer, but as a profession, I spend my life in computation model and at the interface with biology. So, but passion-wise, I was passionate about mass. Mass, 95% atmosphere. So this whole project originally started in our mind in 2010. It was an application for mass. The more we iterated the process, the more we thought about it, the more the challenges of climate change became apparent. We started to work on this battery with another perspective of how to make it superior to existing technologies, how to capitalize on all the assets that such a battery can provide, how many adopters can benefit from it, and ultimately the profitability factor was key at the time. So it was really an iteration process. It started with a hobby, ended up with a company, and basically we consider ourselves a group of dreamers that really push this idea of decarbonization.
That's great to hear. I mean, that's really exciting that it all started with you as a hobby Mars study. Where are you now in your development, Christina? So, yeah, where are you with your battery? Because that hasn't been clear to me, at least here in Paris. Where are you in terms of technology readiness level?
So, if I may, I can share a slide maybe that
sure.
will show better. So everything in this battery, I have to say, is totally new. There are no copycats, so we are doing everything ourselves. So from the day of incorporation, we went through different stages, and each and every stage ended up with an internal division. First, it was the breakthrough catalysis. So what you need for such a battery is a robust catalyst to allow the reaction back and forth for a large number of cycles. Then we went through the bench scale validations, and we apply for our IP worldwide. We did the initial small scale prototype, and now we are at the merger between 200 watts functional prototype, and the next one will be going up to 5 kilowatts prototype. So we are in development between milestone 3 and 4. One detail that I didn't say in this presentation, as fundamentally Agora is an innovation company, so we are seeing ourselves down the road actually establishing a joint venture with battery manufacturers that have the capability and know-how to rapidly scale our largest prototype to a full-size battery. So this is how we intend to actually aggressively enter the market relatively soon. We will not build this battery. We are just developing the prototype up to a unit of 5 kilowatts.
Okay. Yeah, thank you very much, Christina. And we want to stay respectful of your time. And thanks again for getting up early in Canada to share the story about your startup and your venture with us. And next, I believe connected is Kjosta. I'm sorry if I don't speak your name well. Please correct me, from G Batteries, also from Canada, who is working on batteries, as the name of the startup venture tells you already, but on a very different solution. Kjosta, can you hear me?
Yes, absolutely. I can hear you. Thank you so much for the introduction. Pleasure to be here.
Great. So same for you. We have about 15 minutes. And if you could take the first 5 or a bit more to explain your solution to us, and then we will for sure have some questions for you. Thank you.
Yes, absolutely. Let me share the screen with you. Please let me know if you can see the screen.
Looks good.
Give me 1 second, please. Let's try it again.
Looks good.
Can you see it?
Yes, like this is perfect.
Okay, fantastic. Okay, perfect. So once again, thank you for the introduction. Pleasure to be here. Our company called G Batteries, and what we are working on, we are not working on the design or development of the battery itself. We're working with off-the-shelf battery cells. And what we have developed is a software-based charging protocol that enables us to charge batteries faster than any conventional way without damaging the batteries themselves. We started back in 2012. I'm going to rush through this, not to go into too many details. Throughout our process since 2012, we raised 2 rounds of funding. We have leveraged a significant amount of funding from Canadian government. All in all, we have raised about $10 million. We have built our own battery bank device back in 2015 to field test our technology. We have built the rocket ship hardware. We have built the lab where we've tested tens of different types of battery cells with probably tens of thousands of hours of cycles and collected close to 50 billion data points on all of the cells. Demonstrated our tech on a commercial electrical scooter, which is the first small electrical vehicle, working with pilot on the pilot projects with leading car manufacturers and battery manufacturers as well. We plan to demonstrate our tech by 2022 on electrical vehicle battery pack. By the end of this year, we will demonstrate our tech at the manufacturing floor, and we're also on the verge of licensing our technology to a consumer product. So moving on to talk to you about, so that was kind of the backstage foundation of the credibility. Rapidly moving towards the technology itself, what we do and why is it important, and why can't people currently go out and just start charging batteries fast. Battery 101. Any battery out there, whether it's going to be our cell phone, our laptop, our car, we start with 100% capacity. As we charge and discharge the battery, we are losing that capacity due to the irreversible chemical reaction. So the capacity on the vertical axis, the number of cycles on the horizontal axis. After roughly about 600 to 1,000 cycles on the most mainstream batteries, we reach the end of life, which is dictated by the 80% capacity left within the battery cell. When we try to charge batteries faster, we reach the end of life much sooner. So the faster we charge the battery, the faster the battery dies. How it works on the inside of the battery cell is that ions are flowing from one end of the battery to another. The faster we charge the battery, the faster the ions are flowing. The faster the ions are flowing, the more traffic we are creating inside of the battery cell, the faster we are starting to accelerate those irreversible chemical reactions. And there's a number of them. The temperature goes up, internally the resistance goes up, solid electrolyte interface starting to grow, electrolytes starting to decompose, lithium plating starting to appear, and ultimately we can hit the thermal runaway, which is the worst case scenario. It doesn't happen often, but it's still quite possible to do. So in other words, what we envision inside of the battery when we charge it fast, in the comparison, if you take a room full of people and ask everybody to run through the same door all at the same time, you can only imagine what's going to happen. We're going to break the door, we're going to crush ourselves. That's potentially what happens inside of the battery cell. This is just the proof. On the left-hand side, the brand new battery cell. In the middle is the battery cell that has been charged. Commercial grade, fantastic cell, but it was charged 3 times faster than it was designed for. Granted, lasted 300 cycles, very good result, but you can see a very thick mossy layer on top of the surface of the electrode, which is byproduct that we have just discussed. What we have developed is the solution that enables us to analyze the traffic of those battery cells, essentially internal resistance of that battery cell, and modulate the flow of energy into the battery cell. You can envision this as pulse charging, except each and every pulse is different in size, shape, and form. So going back to that analogy where we have ions flowing one at a time without anybody pushing from them at the back, we're giving them sufficient amount of time to take that chemical reaction in a more safer manner. So going back to the room full of people, instead of getting everybody through the door at the same time, we're taking 5 people at a time, 7 people at a time, 3 people at a time, and we're continuously or in organized manner shipping the people through the door while measuring what is that traffic at that door. As a result, what we demonstrated on power cells, which is lithium-ion battery cells you mostly see in electrical scooters, power tools, or drones, we were actually able to charge it just as fast as the red line, and we were able to extend the life of the battery at the same time. For more energy-type battery cells, which we would find in electrical vehicles, we were able to charge it just as fast, and we were able to remain as close to the original life as possible. So continuously being superior over any other conventional way of fast charging. Going to the same picture, same battery cell, charged with the same rate of charge of 3 times faster than what it was designed for as in the middle. But when you look into that battery cell, after 800 cycles, so which is increasing the life of 2.5 times, you could see that the surface was much, much better looking surface of that battery cell. I'm going to skip through this. We have filed over 45 patent applications. We have 14 patents granted, so quite strong IP portfolio on our end. And to wrap it up, to demonstrate what we've done out of the lab is we've took the commercial off-the-shelf scooter, we've updated the plug, we connected it to our charger, and what we have demonstrated is that the scooter that usually takes roughly about 5 hours to charge, we were able to charge it under 10 minutes without damaging that battery cell. So, of course, the next question may come up, well, do you need the hardware to deploy it? What we're working on right now and what we're planning to demonstrate by year 2022 is in fact demonstrated on electrical vehicle battery pack on existing infrastructure for charging and the battery management system. Our goal is to accelerate the rate of charge of electrical vehicles as the first deployment by at least 2 times. And of course, our mission as the company in the next 5 to 7 years is to demonstrate an ability to charge electrical vehicles as fast as it takes to fill up a tank of gas. Hopefully by then the infrastructure will allow us to do that. This is our team, and I'm happy to answer any questions that you may have.
Yeah, thanks a lot for this great presentation, Kjosta. The first question I have is that specific to certain batteries? I mean, is that battery agnostic? Can it be run with lithium ions as well as with other sorts of batteries, or is that not possible as of now?
So we are predominantly concentrating on lithium-ion batteries with the mainstream chemistries such as NMC, NCA, or the consumer electronic devices such as LCO. So mainstream lithium-ion batteries, and not only that, well, first of all, the performance varies from battery type to battery type, chemistry to chemistry construction, energy density, you name it. The performance varies, but so far we have demonstrated that most of the time we are superior over any other ways of charging those types of battery cells. But we're also looking into applying this technology into batteries of the future, as they're being called. Lithium metal, solid state, you may have heard, or silicon anode. We have already demonstrated first preliminary data successfully, and we believe that not only that we're able to enhance the performance of existing current commercial grade batteries, but we would also be able to enhance performance of the batteries of the future.
And how would that in practice and in real be implemented? So would this yeah, basically your charging program that would need to be established on each charging facility, or how do you envision that?
So we are a software-based charging solution. So our first deployment, as we envision this, is it would be based on a software-based algorithm that would be deployed at the battery management level within the vehicle, which would in turn control the charging station on how it would modulate the energy flowing into the car. So in other words, software solution being dropped onto the battery management system inside the car, and then the car talks to the charging station, and the charging station charges that car. So we do not change the charging station, we do not change the car, we are enabling the car to take more energy in. I get asked this question a lot of saying, well, what about all of these fast charging stations and infrastructures around the world that are being deployed? What is being deployed as a fast charging station is in fact the source of power or energy. So the DC fast charging station enables you to get 350 kilowatt, for example. Unfortunately, you cannot put all of that energy into the car because otherwise it will damage the battery cell. And in fact, you may probably know larger car companies are preventing you from a continuous fast charge of the car. Otherwise, they will not allow you to do so if you're going to be continuously abusing the fast charging station infrastructure. So where we come in is we come in between the car and the source of power on the software solution that enables us to allow the car to take all of that power without damaging that battery cell. And our goal is not to play with those infrastructures, is in fact to play with the software to enable, from electrochemical perspective, for the batteries to function.
And have you had feedback already from such companies, like when you approach them and show your solution, are they willing to integrate that basically, then those charging protocols?
Absolutely. We are in active pilot projects with leading car manufacturers around the world, including leading battery cell manufacturers around the world. And we are literally this morning, I have received another draft of the licensing agreement that we're about to sign for a consumer product that we are looking into deploying our technology.
And the biggest challenge that is ahead of you, what is that one? And can Vinci maybe help you? I mean, with that?
Really to demonstrate.
Sorry, go ahead.
Yeah, of course. So our goal is to demonstrate our technology on the actual commercial grade battery pack for electrical vehicles. So that's our kind of ultimate goal that we are striving towards. It will take us another 15 months or so to do. And we believe that once we demonstrate it, we'll be able to overcome any barriers that may be known or unknown at this stage. And talking about Vinci to help us with this is we see from the challenges that were advertised, for example, construction industry, trying to reduce CO2 from the construction perspective and the construction vehicles moving to electrification of those fleets. There's definitely an opportunity there, especially when you need to continue working and you're stuck charging your electrical excavator for the next 8 hours. So there's definitely play there. There's definitely an application there. And we don't need to go right away to the excavator, so we can start with a smaller pilot, but I definitely see an opportunity for us.
Maybe the last question to end this session, is there a limit? I mean, do you still seek to charge faster and to be able to charge more often, to have more cycles? Or do you think as of now with your technology, you have reached the maximum, or is there still development underway?
We definitely see an opportunity to go faster. So right now we haven't reached the ceiling yet. We do see an opportunity. There's barriers from the perspective of requirements, power available, or the BMS or battery management system capabilities. So we haven't reached the limit yet. But I mean, once you, for some of the power cells, once you go to about 7 minutes charge to full, I mean, that's already so fast that it's hard to believe that anybody would want to go faster than that. But we haven't seen the,
I fully agree.
The ceiling yet.
That's a good way to end it. Kjosta, thank you very much for your time and all the best for the future for you and your company. And I think we have the next.
Thank you so much, everybody.
And I think we have the next speaker already connected, Madison from Carbon Upcycling Technologies. So you've seen a bit of their technology and their use case already during one of the presentations earlier today. Madison, can you hear me?
Yes, I can. Can you hear me all right?
Yes, perfect, crystal clear. So again, like for the others, we have 15 minutes together, and I won't stop the time, so feel free to take 5 or 10 minutes to explain better than I did about half an hour ago what carbon upcycling technology does and what makes it so particular. Thank you.
Excellent. Yes, I'll just share my screen here. All right.
Yeah, seems good.
Good. All right. My name is Madison Savlo. I am Chief of Staff at Carbon Upcycling Technologies. We're a startup based in Calgary, Canada, and we take the waste of today to build a better tomorrow. If we were to take the weight of humanity and multiply it by 100 times, that is the amount of CO2 being released into the atmosphere every year. 40% of this comes from the built environment, and we'll see the built environment double in size by 2060. So with that problem in mind, we came up with a carbon utilization solution where we take gaseous CO2 and we sequester it into inorganic solid powders. The powders that we're using they range, but they are industrial waste like fly ash, bottom ash, steel slag, pet coke, things of that nature, as well as natural pozzolans. So things like graphite, talc, yellowstone, and a range of different clays. From there, all of the particles of the powder are acting like sponges. They suck up the CO2 and hold it in place, which then act as building blocks for new materials. So we have about 11 different industries that we can act within, but it is only one platform technology. And by swapping out the solid feedstock, we're able to create different end products. So these are the 4 main industries that we're in at the moment and showing commercial traction in. Our very first product line was an anti-corrosion coating. We sold this first in 2017. We were only 2.5 years old, which made us the youngest carbon utilization company in the world to earn revenue. This is used to coat grease interceptors at the back of fast food restaurants, and we're now working into water and wastewater infrastructure. Another product line is a polymer additive. We use graphitic nanoplatelets, so graphite-derived nanoparticles that act as nucleators in many different types of polymer resins. We're also able to use talc powder and crushed glass for this application. Our third is a CO2 capture membrane that we're currently demonstrating at the Alberta Carbon Conversion Technology Centre. And the most applicable to the concrete or to the construction industry is our concrete additive. So this is the main commercial demonstration that we show at our site at the ACCTC, the site I just mentioned. And essentially how it works is we displace a certain amount of cement in a concrete mix with enhanced fly ash, enhanced steel slag. We use crushed glass, many different types of powders, and those are able to increase the compressive strength of the concrete. So I'll talk a little bit more about that mostly. This is a very, very standard concrete supply chain. The fly ash will enter into the concrete supply chain either in the precast concrete or into ready mix. So we're able to work into both markets. You can see where our unit would be placed is on the back end of this. We process the typically fly ash or other types of powders, and it'll then enter into the stream so that all of the concrete supply chain stays intact. We understand that the concrete industry is very conservative, it's slow moving, so we wanted to make sure we had a plug and play technology that allows for easy adoption. In most cases, we're able to replace up to 20% of cement in a concrete mix, which then increases the compressive strength of concrete by about 40% using our additives. That's about a 6 to 10% cost reduction, and it also reduces the greenhouse gas impact by about 25%. Because we sequester the entire CO2 molecule, we're also able to keep our process low energy. We're able to also tailor to non-peak electricity hours through a batch run process. So over the past 6 years, we've scaled our technology over 10 million times. You can see there the alpha reactor is quite small. It's actually about the size of a cookie jar. And we've just commissioned this year the ADA reactor. It does produce between 8 and 20 tons per batch, running for between 4 and 8 hours. So it is a large demonstration that we're showing at the Alberta Carbon Conversion Technology Centre for our demonstration at the Carbon X Prize, which is a big global competition we were a part of for the past few years. We're now looking for licensing agreements and demonstration opportunities for larger units, which would range from 50 tons per day all the way up to 200 tons per day. We want to make sure that the supply chain is intact, so we want to see these reactors put directly at a manufacturer's site. Right now, our site is located at a natural gas plant where we're taking the CO2 directly from the flue stack there and into our units. So we wouldn't be where we are today without our amazing partners. These are just a few users of our anti-corrosion coating. We do have some big brand names that are using this in their restaurants, but mostly the customer that we sell to are contractors. So one of our major customers is Oldcastle Precast. They're based in Florida, and they're one of the largest precast companies in the US. Our bigger partners across our corporates, our universities, and then just research and government bodies range from Burnco. They're a local concrete supplier in Alberta who's agreed to take all of their supply of enhanced fly ash from our largest reactor. We've recently partnered with CMEX Ventures, which is really exciting to see our technology being uptaken into their product lines as well. In 2018, we graduated from the Lafarge Wholesome Accelerator, and we've been working with them steadily since then. And just recently, I guess this last month, we were noted that we are now accepted into the Vinci Accelerator program. So we'll be a part of that as well. So our awards, as I mentioned, we are a part of the Carbon X Prize, which is a $20 million global competition for carbon utilization. We have completed that competition now, and we're just waiting for the results. So those should be released between April and July of this year. So stay tuned for those. We've also received a Solar Impulse label, which is quite exciting. It is only awarded to 1,000 clean tech companies worldwide. And we've also, a couple years ago, been awarded from the 76 West competition funding to start up operations in New York State. Our management team, our founders are Apoorv Sinha and Greg Bozer. We also have a third founder that's more passive, but in addition to our technology growing, our team has grown as well. We have about 6 full-time employees on staff, and we deal with a lot of contractors on a daily basis. So where we don't make up for an internal capacity, we have an incredible ecosystem that we operate with on a regular basis. We're creating versatile, high-performing solutions that make sustainability easy. These range from infrastructure solutions to advanced materials, all the way down to carbon capture and energy solutions. So I'd be happy to talk about this more and to see where we can integrate our technology and our solutions into your cities. Thank you.
Yeah, first of all, congrats, Madison, to all the recognition and to the acceptance in the accelerator program. It sounds really exciting. Question from a non-material scientist. Can you tell me what makes a good sponge? So I know you had the examples that you currently work with, but can you elaborate a bit more? What is good for enhancing or enhanced CO2 absorption?
Yeah, that's a really good aspects to it, but we've tried pretty much any inner powder is able to work within our reactors. It is the same process, but we can tailor some of the environment around it, whether that's the pressure of the CO2 to make sure that the CO2 is being absorbed, as well as the amount of time that we're actually processing these materials for.
Okay, and when we think about the end of the lifetime of your materials, I mean, do you think special recycling will be needed because it stores additional CO2? So what happens at the end of the lifetime if it degrades? Have you foreseen anything in particular regarding recycling?
Yeah, this is an excellent question. It doesn't affect the recyclability or the end of life compared to what the conventional material would be. So for instance, concrete would be disposed of in the same manner. Same with plastics, they can be recycled just the same way. For plastics, the only caveat there is that our CO2 does release with temperature, very high temperature, that being. So incinerating the plastics would release the CO2, and that's really not acceptable. So we make sure that we're working with plastic material that doesn't go into an incinerator process, namely bioplastics and things like that. That's really our end goal there. When it comes to the concrete, that will be stored in a stable form indefinitely, as long as the concrete doesn't reach high temperatures, which it typically doesn't.
Okay, understood. And I mean, from what you showed us, the adoption seems very easy. I mean, you made the adoption for the industry very easy, but what's the feedback you got so far? I mean, also regarding performance, right? Concrete is such a, yeah, I mean, it's used in so many constructions and so sensitive part of it. So does the industry like any modifications? Is it hard to convince them or actually fairly easy?
Yeah, this is another really great question. Typically what we've seen is that the adoption in that sense is very simple. Fly ash has actually been used in the concrete industry for pretty much centuries. It's always been a part of the mix to reduce the amount of cement use. The difference with ours is that we process it first. We make sure that all of the particles are the same size and we embed them with CO2, which is where we get the performance enhancements. But because fly ash has been used for so long, it's already in regulation and we don't need to get any additional approvals or anything to embed this into the concrete. So from that standpoint, it's fine. From the standpoint of performance, we have been doing a ton of testing with very large corporations such as Burnco, Lafarge, Cemex. We're making sure we use these brand names to actually get the validation of our products. And we haven't had any issues with that. There's actually been improved compressive strength, as I mentioned, up to about 40%.
Okay, and for the flue gas that you use as CO2 source, is your solution kind of flue gas agnostic? Do you need to run kind of tests on the composition of that flue gas, or can you use that from any industry without any purification, or is there some workup processes in place for the flue gas before it can hit the sponge?
We call ourselves CO2 agnostic, actually. So it's not directly the flue gas that we're using. It would need to be processed to about at least 80% purity. That being said, as I mentioned in the presentation, we have a Co2 capture membrane that we're able to use to filter out the CO2 to that purity. So that's really not a problem, but we can use, a flue gas from any type of industrial source. It does a little bit make a difference what the composition is, but it's typically not a problem for us to filter that out. We can also use direct air capture CO2. We've received that in tanks, as well as industrial grade CO2.
Okay, and do you have anything like also in terms of challenges ahead of you that if you had a wish-free like Vinci could do for you, anything that when you look at their business, you would look forward for on collaborating or on getting expertise or anything in this regard?
Yeah, I think the biggest wish for us, being in such a conservative market such as concrete, is just to have those connections being made to other large concrete manufacturers. We've been quite successful so far being able to reach a few of the big players, but of course there's many more concrete producers that we can be in touch with. Concrete being the second most used substance in the world other than water, it's an incredible opportunity for us to demonstrate this technology in multiple regions of the world.
Okay, then maybe one last question from us here to end this session with you, Madison. So when thinking about scaling up, you said that you have a 5-ton, right? That is proven, that is what you have in the pocket, and you aim for 50 and 200 now. Is there any challenge you foresee when scaling up, or is that basically just a matter of needs of market as soon as you have the right clients that would take your enhanced materials that you can build more?
Yeah, for sure. I know our 20 ton per day reactor is really a commercial demonstration of what we can do. Of course, that's not directly at scale of what a concrete manufacturer would use. It is more in the terms of 100 tons per day. So that's really what we're looking to do next, is find licensing agreements where we can show this directly at a concrete manufacturer's site. And that'll allow us to scale a bit more rapidly.
All right, thanks for this conclusive answer and your time. You've been the third speaker from Canada here, so it's really great to see that there's so much innovations going on with a sustainability angle in Canada. And yeah, thank you, Madison, and all the best to you and Carbon Upcycling Technologies.
Yes, thank you so much for having me.
And the very last speaker of today is Sissy from Metalmark Innovations. Sissy, are you connected?
Yeah, can you hear me?
Yes, perfectly.
Yes.
So you have the great honor to close this evening here at Leonard. And the same for you. You have about 15 minutes, so please take 5 to 10 to explain a bit about your innovation. It hasn't been mentioned so far, so really people are not aware of what Metalmark Innovations are doing. So take it easy and take it slow, and convince the people about your work. Thank you.
Thank you very much for the opportunity. I just shared my screen. Are you able to see that?
Yes.
Excellent. And, I also wanted to thank the group for the sponsorship of Hello Tomorrow and the competition and the Smart City track, which we were very pleased to win. So yes, my name is Cece Liu. I'm the CEO and co-founder of Metalmark Innovations. And at Metalmark, we make indoor air cleaner and safer to breathe. So according to the US EPA, we spend 90% of our time indoors, where we're surrounded by air pollutants from viruses like coronavirus to VOCs like formaldehyde and ultrafine particulates. These pollutants are less than 1 micron in size, and they make up 80 to 99% of indoor air particles. According to the US National Institute of Health, these pollutants decrease cognitive function, they cause cancer, trigger heart attacks, and lead to a whole bunch of other diseases like dementia and DNA damage. Meanwhile, the lack of cost-effective and safe solutions for eliminating airborne viruses will limit our ability to prevent future pandemics. At Metalmark, we leverage our nanomaterials inspired by butterflies like the Metalmark that you see here to create air purification systems. Nature achieves high and multifunctionality through nanoscale architecture of simple materials. This is particularly true in butterflies. Their wings are iridescent, light, strong, and water repellent, achieving all of this through nanostructuring an organic material called chitin. So we took the same design principles and created our materials using metal oxides and metals, which are very, very well known and industry is very comfortable with. By doing so, our materials become catalysts that can break the bonds between atoms and completely destroy air toxins without the creation of secondary pollutants. Our air purification system is designed to seamlessly integrate into indoor spaces, and we engineer them around the Metalmark cartridge that is responsible for turning submicron pollutants into breathable air. At the heart of the Metalmark cartridge is an active coating of our proprietary material. This patented coating material catalytically breaks down chemicals at the molecular level and inactivates viruses. Our platform nanomaterial technology is highly adaptable and can be applied to many other applications, such as emission control, chemical conversion, and fuel cells. Because of this, the market opportunity for our products spans multiple verticals, from special coatings to conventional catalysts, totaling $260 billion. We're first targeting the air purification segment, a $13 billion market with an initial beachhead of $100 million. We have signed agreements with customers to begin demonstrating our air purification product in a customer pilot. In parallel, we're working with partners to bring our technology into other verticals, as I mentioned, such as smart coatings. Our success would lead to $1 billion valuation potential. But at the end of the day, what's remarkable about Metalmark isn't just our technology. It's also our world-class team. My co-founders are experts in material science with PhDs from the Weizmann Institute of Israel and served as postdocs at Harvard University. They each have over a decade of experience in leading technology development. I bring nearly 20 years of experience in launching companies and investing in clean tech. I managed Massachusetts Clean Tech Seed Fund, built partnerships with companies like Audi, and helped to raise over $100 million for clean tech startups. In addition to our core team, we benefit from the guidance of a committed advisory team made up of leading figures in the science and industry at organizations such as Harvard, MIT, BASF, and Aspen Technology. Since our founding, we've raised venture capital and non-dilutive grants and awards, secured IP, and demonstrated customer traction. So Metalmark's mission and products are well aligned with the Vinci Group's vision and businesses, specifically in bringing about the future of sustainable cities and living through addressing wellness, building energy efficiency, and climate impact, even making shared mobility a more pleasant experience. We're open to engagement and collaborations in various ways, such as conducting demonstrations or integrating our products into the Vinci Group's projects or building materials, as well as strategic partnerships or investments. We hope that you'll join us in bringing about a sustainable future together.
All right. Thank you very much for your presentation. A couple of questions before we end this evening. So one is about the lifetime. So can you say something about this? How often do you need to then change the device, the filter?
Sure. As I'm sure you know, one of the big problems in that's kind of arising with air quality now, indoor air quality, is the use of throwaway non-woven filters. And these have to be generally replaced every 3-4 months, especially the HEPA grade, ULPA grade materials. And as we live through COVID, this is becoming more and more of an evident problem. And so we actually believe we have a huge advantage in this area. Our material has been tested to be very, very stable over long periods of time under very harsh conditions. And so we believe that it is suitable for use for 5, even 10 years. And this material can be regenerated, which is difficult to do with other types of materials. So, you know, getting to sort of the idea of zero waste or minimizing waste from material from a product perspective are very, very important to Metalmark and how we view our sort of participation in this endeavor.
And you mentioned COVID. So was COVID and the current pandemic we are in something boosting your business or also challenging you, because I guess many new competitors are emerging with this pandemic around?
Yeah, it's a good point. Initially, when we, we are still an early stage startup. So when we first encountered the pandemic, there was a lot of enthusiasm around our technology, but at the time we didn't have a product yet. And so we're in that, actually, we have been building our prototypes and testing those. But in the meantime, as you alluded to, many other competitors have entered the market, making claims about their efficacy. And these really fall into a few categories. One is, again, general filtration using HEPA or other high-grade non-woven materials to filter out viruses or microbials. And there are definitely limitations to that, and not to mention high capital and operating costs associated with this type of approach. Another that's emerged is bipolar ionization, which has been frowned upon because of the generation of ions, which has longer-term damage and impact on health. The third is UV, so UV being used inside of air ducts versus being just installed into our indoor environment. And then finally, so UV, has its challenges. You have to have a very long residence time for it to work. As a way, essentially, you would need to filter any type of microbial and other organisms, and use UV to deactivate them over minutes or tens of minutes. Installing UV into our indoor environment has a long-term impact on health as well, damages to tissue. And then finally, there's there are other types of categories of technologies, such as photocatalysts, which have been shown to generate a lot of secondary pollutants, meaning that in the process of breaking down toxins, they actually generate additional ones as well. So we believe that we still stand very, very unique in our technology in terms of efficacy, not generating secondary pollutants, and having potential to reduce our waste to the environment.
Great. Yeah, I hope that you prevail in this now fairly crowded space, but it looks like you have a clear competitive advantage. One question, you just mentioned it briefly in half a sentence. You're also looking into coatings. So how do I have to imagine that? Is that then with the same application, air purification, or can you a bit elaborate on that?
Sure. So if we go back to the concept for the platform technology itself, it is creating that sort of lattice-like three-dimensional structure using metal oxides and metals. And so this can be applied to a variety of applications beyond air purification and catalytic functions. Namely, we can create different types of smart coatings, create other effects in the process. So there's a lot of different things we could do with this type of coating material that has implications for the future of building materials that we haven't talked a lot about in general, but we're exploring with partners about it.
All right, Sisi, thank you very much for your time. We are about to close this evening, so thanks for tuning in and presenting Metalmark Innovations.
Yeah, thank you very much. I really appreciate it. If you have any questions, please feel free to follow up with me afterwards.
Yes, we definitely will share all the contact informations, and I think also internally at Leonard, this will be available for replay and send around. So thank you again, and I welcome back on stage Mathieu from Leonard, who will have some closing words for us for this night. Thank you.
Thank you.
Thank you, Nicolas. Thank you to all. Thank you for joining us tonight, and thank you for following this summary of what could have been the Global Summit in Paris this year.